To finish with our study of integration via partial fractions, we're looking at the case where we have repeated irreducible quadratic factors, and as we will see, this can get pretty nasty. So if the factorization of the denominator contains a repeated irreducible quadratic factor, something of the form ax squared plus bx plus c to the n, where ax squared plus bx plus c cannot be factored any further, which means b squared minus 4ac is negative, then the decomposition into partial fraction will contain the corresponding terms, a linear function over that irreducible quadratic factor, plus another linear function over that irreducible quadratic factor squared, and then we have one such term for each power of this irreducible quadratic factor, from 1 all the way to power n. So the problem becomes to integrate these type of terms, a linear function divided by an irreducible quadratic term to the power k. So how do we do that? Well, we pretty much follow the steps that we have outlined for the case where k is 1, in other words, for the case where it's a non-repeated term. But practically, it will mean a lot of complications. Specifically, we start with completing the square. So we factor out a, when we pull it out of the power k, we get 1 over a to the k, and then we have this x squared plus b over ax in which we complete the square. So we take 1/2 of the coefficient of x, so we get something that looks like that, where alpha is some alpha squared correspond to some positive term. It doesn't matter exactly how it is in terms of a, b, c. And then we take the substitution u equal whatever is under the square, and we get something that roughly looks like that, a linear function in u over something of the form u squared plus alpha squared to the k. In this, we're going to do what we've done again in the case where k was 1, that is, split the fraction. On one end, we're going to need to integrate u over u squared plus alpha squared to the k, and on the other end, 1 over u squared plus alpha squared to the k. In the first case, we can proceed as before. At the top, we have u du, and at the bottom, we have a power of something of the form u squared plus alpha squared, whose derivative is 2u du. So in other words, if I set v equal u squared plus alpha squared, I get 1/2 integral of dv over v to the k, and that can be integrated. So we have no problem with this part. The problem starts with this other part. In the case where k was 1, we had a formula with arctangent to integrate this. However, now we don't have this formula available, and what we need to do with that is use trigonometric substitution. And as you know, this can be quite long and require a lot of calculations. We've done such an example at the end of the videos, instructional videos on trig substitution in Module 5. So what do we do in this case? Well, we're going to use a trig substitution. U is alpha tangent of theta, then du is alpha secant square theta, and we substitute. So at the top we have du, that's alpha secant square of theta. At the bottom we have u square is alpha square tangent square theta, plus alpha square, all that to the k. I can pull out the alpha square, and when I pull it out of the power k, I get alpha to the 2k. I can pull out the alpha that is at the top. I get a constant term, alpha over alpha to the 2k, and then the integral of secant square divided by tangent square theta plus 1 to the k. And the point of this trigonometric substitution is that tangent square theta plus 1 is really just secant squared of theta. So at the bottom I really have secant of theta to the power 2k. So in other words, after simplification, what I'm integrating is 1 over secant to the 2k minus 2 which I can write as cosine theta to the power 2k minus 2. And now it comes down to integrating an even power of a cosine or a sine, and we've seen how to proceed with that using the double angle formula in module 5, at the beginning of module 5. So specifically we're going to write that as a power of cosine square theta and replace cosine square theta using the double angle formula by 1 plus cosine of 2 theta over 2. Then you multiply things through and potentially iterate this process until you have no powers left. So if k is large, this can be quite painful, and additionally at the end we get a function of theta and we have to go back to a function of u first and then as a function of x. So this is a fairly long process potentially. We're going to look at a couple of examples. First, we're going to look at an example where we're lucky and we don't really have to worry about this trig substitution. And then we'll look at a case where we need to do the trig substitution, and that will illustrate that it is theoretically always possible to do it, and practically quite difficult if you have to do it by hand. So let's look at the integral of the function 1 minus x plus 2x squared minus x cubed, all this divided by the product of x with x squared plus 1 squared. The degree at the top is 3, the degree at the bottom is 2 times 2 plus 1, so 5. So the degree at the bottom is higher, so we don't have to worry about long division, and we can just write out the form of the decomposition of this function into partial fractions. In this case, the factored form contains one non-repeated linear factor, x, and to this corresponds a over x. Then we have one irreducible quadratic factor, x squared plus 1, that is repeated twice. So we get two partial fractions, bx plus c over x squared plus 1, and dx plus e over x squared plus 1 squared. One for each power of x squared plus 1, from 1 to 2. And now we need to find these coefficients a, b, c, d, e. And to do that, we're going to rewrite the right-hand side as one fraction and identify the numerators. So if I multiply things through, you see that to write the right-hand side as one fraction with denominator x, x squared plus 1 squared, I need to multiply top and bottom for the first term by x squared plus 1 squared, so I get a x squared plus 1 squared. For the second fraction, I need to multiply top and bottom by x and by x squared plus 1. That's why I get bx squared plus cx times x squared plus 1. And for the last one, I need to multiply top and bottom just by x, so I get dx squared plus ex. So now we can identify the numerators, and I just multiply things through in x squared plus 1 squared, and then look at what I have for b. Bx squared is multiplied by x squared plus 1. In other words, b is multiplied by x to the fourth plus x squared. Similarly, c is multiplied by x cubed plus x. And now I can reorder the terms to look at the monomes of each degree. Right? What is the coefficient of x to the fourth, of x cubed, of x squared, and so on, and identify the coefficients of corresponding degree, since we have an equality between two polynomials. So if I do that, the coefficient of x to the fourth, you see that it is a plus b. We have only one term in x cubed, it's cx cubed, and for x squared we have 2a, b, and d. As for x, we have cx and ex, and the only constant term is a multiplied by 1. If now we identify the coefficients of corresponding degree, we see that a plus b should be 0, c should be negative 1, 2a plus b plus d should be 2, c plus e should be negative 1, and a should be 1. So these are the conditions. You see that a is 1 and a plus b is 0, so b is negative 1. C is negative 1, and therefore we can also find d and e, because d is now 2 minus 2a minus b, and we have found a and b, and e is negative 1 minus c, and we have found c. So this way we find a is 1, b is negative 1, c is negative 1, d is 1, and e is 0. So that means that we can replace the coefficients by these values in our decomposition into partial fraction, and this is what we obtain: 1 over x plus negative x minus 1 over x squared plus 1 plus x over x squared plus 1 squared. And so this is what we want to integrate. One of the steps that we indicated in how to deal with these types of partial fractions was to split the fraction whenever possible. So this negative x minus 1 over x squared plus 1 is split into negative x over x squared plus 1 minus 1 over x squared plus 1. And now we're going to use the change of variable u is x squared plus 1 in order to integrate the second and fourth fraction in this sum of 4 fractions. So in that case, du is 2x dx, so we're going to replace x dx by 1/2 du, and so we obtain for the integral of dx over x corresponding to the first fraction. Then we have minus 1/2 of the integral of du over u minus dx over x squared plus 1 plus 1/2 integral of du over u squared. So for the integral of dx over x, we get just natural log of absolute value of x. Here we're going to get negative 1/2 natural log of absolute value of u. For this fraction, we can use our formula with the arctangent. Here, this is really just arctangent of x. And for this last term, we have the integral of u to the negative 2. So we get u to the negative 1 over negative 1. In other words, negative 1 over u, that we multiply by 1/2, it's going to give us negative 1 over 2u. So this is what we obtain, and u was x squared plus 1, so we can just replace it, and we obtain explicitly our antiderivative of the function. So this was not too bad, and specifically was not too bad because the coefficient e was 0, so the particular term where we would have to use trigonometric substitution disappeared. Now let's look at an example